Hi, and welcome to a quick paper review and discussion of our submission for NeurIPS 2024 workshop for the adversarial machine learning track, seeing through the mask with thinking adversarial examples for CAPTCHAs. So, to start off, I'd like to give you a quick intro to adversarial machine learning, specifically adversarial examples in computer vision. And then we'll dig deeper into the specifics of the paper, our results, and some intuition that we've got throughout the paper review journey. So what is an adversarial example in computer vision? So you have an input image X, a perturbation, that you can then apply on X with an arbitrary intensity epsilon. With the only constraint should be that you aren't allowed to have semantic loss of key features that make the image unrecognizable to humans. This is, of course, hard to measure. You usually have some kind of threshold. And you can actually quantify that, and we'll come to that in the next slide. And then you have the classifier that is trying to fit itself to the human perception function, which is implicit, and that we can't actually quantify. And we only generate test sets that allow us to approximate it, but the discrepancy between these two functions and models is actually what allows misclassifications that are targeted based on the perturbation. So an adversary can just say, okay, so I know where the human judgment and the classifier are further apart, and I'll exploit that discrepancy to cause misclassifications through superstimuli, such as this noisy image. So you have an input, you apply the perturbation, and although the input and output both look the same, the perturbed input, the classification has completely changed. Of course, this is just a very simplistic example, and it could be applied to all kinds of computer vision models like detection tasks, semantic segmentation, etc. But this is just an example to get started, which isn't too exciting. And talking about semantic similarity, where we set a threshold, here we have LPIPs with the original images and some perturbed patches with different epsilon. So here we have the chin of presumably a man that is shaved, and we do see key features such as the nose and the lips in almost all the variations, and we can set a threshold after which we could assume that most people aren't actually able to differentiate the images from each other. So now I'd like to share a perspective, or an intuition rather, that I've gotten after going through a bunch of adversarial machine learning papers this summer. So I believe that the robustness versus accuracy trade-off is a wrong perception of what adversarial robustness actually is. So there are papers on a theoretical principle that explains why adversarial robustness and model accuracy contradict each other, and others that say that they could be reconcilable through a proper definition. But this is, this whole field is quite new, and there are many contradictions within different research teams. So we don't actually know what the real reason is between the discrepancy between human and model vision that can get exploited, and we also don't know why usually more robust, adversarially robust models have lower accuracy, because you would assume that the features shown previously are robust enough such that they generalize from the train set to the edge cases that we reach with the perturbations. So my hypothesis is that adversarial robustness is actually a much better metric for generalizability than our classic test set accuracy, and it actually does really pay off to sacrifice accuracy as what we really care about is the model's generalizability in downstream tasks and not just some arbitrary metrics to one-up each other in papers. And this is and also you can get the best of both worlds if you do it smartly. So here we have a paper by Matthias Lechner from the ISTA, and he figured out that for a specific configuration you can actually both increase accuracy and adversarial robustness at once without having to sacrifice anything. So this is a really exciting field, and I really hope that in a not so distant future we can find more realistic metrics on how we measure our model's performance. And I think this quote by Charles Goodhart captures it well. When a measure becomes a target, it ceases to be a good measure. And yeah, this is like this one funny XKCD meme where you just have this soup of linear algebra and just stare around and try to optimize metrics without thinking of the applications, interpretability, and downstream tasks, which is obviously a hyperbole, but just an interesting comic that captures the spirit of what I've said quite well. And this tweet as well. So since 2013, where we found out about the existence of adversarial examples, we still, in some sense, have made a lot of progress in quantifying or robustifying models and figuring out what the source of the problem is and how to patch or resolve or mitigate the vulnerabilities that we're encountering across all models, because these properties are transferable across all kinds of models. So how did we actually apply this in our research? We thought, okay, so we can actually exploit these vulnerabilities of models that we've just encountered to differentiate humans and machines better. So we built a replica of reCAPTCHA v2 that allowed us to have like some kind of online testing framework. So all of this isn't actually connected to the Google servers. This is just local and helps us to run experiments in a realistic environment. And this is a classic CAPTCHA example, as you probably know it. And the next step was just to find very, very simple adversarial attacks that we could apply on our data set. So we found HCAPTCHA, and they had some really, really simplistic examples with masks that have geometric forms like circles, diamonds, and squares. And we also made our own knit mask. And after reconstructing them with a rendering engine, we just found optimized our hyperparameters, found the best performing mask with the optimal opacity and density. Density being the number of geometric objects per row or column, and the nesting count. Then we also combined it with the classic attacks such as FGSM and figured out that the combination actually isn't fruitful, especially when you apply the attack after, on top of the mask, which was interesting. So we only solely focused on using the geometric masks, which is super simple, very straightforward. And then we defined our own quality metric, semantic quality metric, which is based on cosine similarity, PSNR, structural similarity, and LPIPs, as mentioned previously. We weighted the sum, and then we measured the delta of the accuracy rank of the model on the original versus the perturbed image. And ideally, we would want to have an image that, ideally, we would, in the best case scenario, we would like to have data sets that look the same, but are a lot more aggressive. So the structural similarity should be the same. It shouldn't be any harder for humans, but a lot harder for machines. This is what we're measuring in the final score. We also made a robustified model that actually didn't perform as well as thought, because it was based on these not so well performing values, which is something we didn't include in the paper, but would be interesting to look into at a different time. And this is like the, kind of final conclusion of the paper on regarding the generalizability of the models. So we just took the best performing hyperparameters and tried to figure out what the golden spot is between maintaining the structural features as well as reducing the model's performance after the perturbation. And this is a logistic axis, so don't be confused by that. It's just linear regression. So you've found that they correlate, and that by applying mass and taking away key features, models perform worse, which makes sense intuitively. So where do we go from here after having found all of this out? So something that most adversarial machine learning papers actually don't mention is that these perturbations also impact humans when they're time constrained. And something that would be really interesting to explore further is exploiting the high sensitivity of the human judgment function towards pets, hazards, and food, and also the speed of reaction time. So human perception is optimized for survival, and we're super fast at detecting danger. And this is something that definitely could give us an edge. We could look into that in differentiating ourselves from the computer vision models out there. And also through image generation, we can create completely novel out of distribution images that still have like some surrealism and resemblance to the real thing, such that they're useful for visual question answering, but need like a lot of creativity. And for example, we could generate a bunch of images and request a storyline for the bot or human to answer. And also there's this super new recent paper by Stanislav, Ensemble Everything Everywhere, which is about downsampling images before putting them in, and also self-ensembling. So as it turns out, different layers of computer vision models are show different robustness towards perturbed images, which is very interesting. So apparently only the final layer shows sensitivity, and by using intermediate layers, we can increase the robustness by a wide margin without any kind of additional overhead. So yeah, that's a quick summary of what I've been up to this summer, what I've learned, and our results. Thank you for listening, and I'd also like to thank my supervisors, both at the ETH Zurich and at TU Wien, and Tolan for collaborating with me, and Stanislav for providing a super awesome, and Balaji super awesome introduction to this topic for me. And yeah, just a bunch of links to all my side quests on this journey. Thank you for your time.